Hello everyone, welcome to the session Impact of Free Jets. First, we'll see what is impact. When the force is acting for a short interval of time, that we call it as impact or impulsive force. And the next, what is free jet? A fluid jet is a stream of fluid issuing from a nozzle with a high velocity, hence high kinetic energy. What is kinetic energy? It is like half m v square, right? That means your velocity, as your velocity increases, your kinetic energy also increases. Is it right? Next, when the jet impinges on a plate or a vine, it exerts a force on it due to the change in movement. What is momentum? What is momentum? Mass into velocity is your momentum. And the next, what is change in momentum? The initial minus the final momentum is your change in momentum. And the next, this force can be evaluated by using impulse momentum principle. What is impulse momentum principle? The force is equals to mass per second into the velocity, and that's your impulse momentum principle. And moreover, this impact of free jets work on the principle of impulse momentum. Impulse momentum. Just clear it. And the next one. So in these we have two main cases. The first one is the force exerted by the jet on the stationary plate, and the second case is on the moving plate. Okay, the first case is stationary plate and the second case is moving plate. Okay, in this session we'll go with a stationary plate. In the second session we'll go with a moving plate. So in these we have flat plate is held normal to the jet, and the flat plate is held inclined to the jet, and the third one is plate is curved. Okay, just like this. Okay, and the next one, in this curved plate we have three cases. The first one is the jet strikes the curved plate at the center, and the next one, the jet strikes the curved plate at one end tangentially. Here the curved plate should be a symmetrical one, which is like a symmetrical one. And the third case, the jet strikes the curved plate at the end tangentially. Tangentially is nothing but tip. Here you can see here, right? This is your tip, and here your jet is take place, and that we call tangential. And here the plate is unsymmetrical. Clear? Unsymmetrical. We'll see what is symmetrical and unsymmetrical and in the coming sessions. Clear? And now coming to the second one, the force exerted by the jet on a moving plate, and this we'll discuss in the next session. Clear? And again in these we have three cases, which is like a previous one: the normal jet, inclined to the jet, and the plate is the curved. For this curved we have two cases, and in single case we have two sub cases. Again, here the first case is just strikes the curved plate at the center. And in these we have the single vane, and we have series of vanes, which is like a simple example is your Pelton wheel. And here they just strike the curved plate at the end tangentially or at the tip. We can call it as tip. Okay, and this is unsymmetrical one. Clear? Unsymmetrical means, okay, the plate like it won't divides like a two halves. Clear? Like it will be like 1/3 Okay, 1/3 of the blade to this side and the 2/3 of the blade will be to the this side. Clear. And the next, again in these we have two cases, which is like a single vein and the series of radial veins. Clear. But now here we are seeing with moving plates, but we'll in this session we'll go with only stationary plate. In the next coming sessions we will go with the moving plates. And now the force exerted on a stationary plates. We'll see these stationary plates and the moving plates in the next session. And plate held. This is your first case in the stationary plates. Okay, this is normal to the jet. First we'll see here, and this is your nozzle with the diameter d. Okay, and this is your plate, and the next one, this is your stationary plate, which is like a normal to the jet. Okay, we can see the jet here, and which is of dia d, and this is your axis of jet, and from the outlet of your nozzle we have the velocity of jet, which is like v. Clear. Next, after impinging on a flat plate, okay, it will turns to 90 degrees, which is like it will exit in the y-axis. But in solving the problems, we require the outlet velocity in x direction, but not in y direction. Clear? Okay. Now how to solve this? According to the impulse momentum principle, the formula is force in x direction is equals to mass per second, which is like m dot, okay, m dot into velocity of jet before striking the plate, which is like v, minus velocity of jet after striking the plate. That means we require the velocity in x direction, not in y direction. Clear? Yes. Next, mass per second, which is like m dot equals to rho av into the velocity of jet at inlet, or else before striking the plate is v, and after striking the plate, that means in this direction there is no velocity, so that's why it is 0. Okay, the final one, the force exerted by the jet on a flat stationary plate in the x direction is rho av, rho av square. Clear? Okay, and the same principle you are going to follow for each and every topic or subtopic or any case. And even in this chapter, if you want to solve any problem, in that we have to follow only the impulse momentum principle. Clear? And next we'll see the second case, which is like when the plate is inclined to the jet. Okay, this is your plate which is inclined to the jet, and now your force has to act in this way, but because of this inclination, actual force which is like normal to the plate is this one, which is like Fn. Clear? And now what is the angle that is making with the jet? It is like theta. And now the mass of liquid per second striking the plate is equals to rho av. We know that from applying impulse moment equation, the force in normal direction is equals to rho av, which is like m dot, right, m dot into, and what is this? The velocity before striking the plate. What is the velocity? See, this velocity component in x direction component is v sine theta. For that you can see the figure here. Clear? This is v sine theta. And next, this is the velocity after striking the plate. In this direction there is no velocity, so for that it is like 0. And finally what you're going to get is Vn is equals to OA v square sine theta. Clear? And now for this we required the force in x direction, the force in the y direction. What is x direction? Parallel to the direction of the plate. jet, and it is normal to the direction of the jet. Clear? So for that, so from this given figure, you can say that fx is equals to fn sin theta, fy equals to fn cos theta. If you resolve this, what you're going to get is rho a v square sin square theta, rho a v square sin theta cos theta for y. Clear? And the next we'll see for third case, which is like for curved plate. In curved plate we have three cases, right? The first case is the jet strikes the plate at the center, and the next case is at the tip when the plate is symmetrical, and the third case is at the tip when the plate is unsymmetrical, right? So in this case, you can see the nozzle here, and this is the jet, and this is your curved vane. Is it right? Curved vane. And now the jet is striking at the center, and now to say whether it is symmetrical or unsymmetrical, you can see here angle is there. But here the angle is there, which is like theta, right? This is theta, and this is also theta. If these two angles differs, then we can say the vane is a unsymmetrical one. But here it is a asymmetrical one. And in the same way, first we'll see the velocity in this direction is v. After striking the plate, it will moves like in some angle, which is like again at theta. The outlet velocity is v, but the actual velocity in x direction is v cos theta, in y direction is v sin theta. Now the component of velocity in the direction of jet is equals to minus v cos theta. This is minus v cos theta. Why? Because this velocity, the inlet velocity is in this direction, and the outlet velocity is opposite to the initial velocity. So that's why it is like v cos theta. And the component of velocity perpendicular to the jet, this is like v sin theta. The force exerted by the jet, which is like fx, is equals to from the impulse momentum principle, it is like mass per second, which is like rho av into v1x. That means the velocity of jet before the striking the plate in x direction. This is the velocity of jet after striking in x direction. And before striking the plate, we have the velocity v, right? We have velocity v. And after striking the plate, we have the velocity like minus v cos theta, right? Minus v cos theta. And if you simplify this, what you're going to get is fx is equals to rho a v square 1 plus cos theta. Clear? Now similarly, for y direction, the force in y direction, okay, that equals to mass into mass per second, which is like rho av, the velocity before striking the plate in y direction, the velocity after striking the plate y direction. Before striking the plate in y direction is 0, and v sin theta, which is like after striking the plate, this is your velocity, which is like v sin theta. And if you simplify this, you are going to get fy, which is like force in y direction, is equals to minus rho a v square sin. Clear? We'll see the next case. This is the second case, which is like jet strike the curved plate at the end tangentially, which is nothing but here, the tip, okay, tip of your blade. And here the blade is symmetrical. What is symmetrical? See, from here, if you take a line, right, here the angle is theta, and now from here, if you take a line, this angle is theta. Clear? And now if these two angles are theta, then it is a symmetrical one. Now the jet is striking at the tip of the plate, So it is like some inclined with the horizontal, which is like theta here. Okay, you can see here the theta, and here also it is like theta. That means these are similar alternate angles, or we can call it as similar triangles. Okay, and now the velocity in x direction at the tip or at the starting position is your v cos theta. In y direction at the initial stage, it is like v sin theta. That means if you resolve this velocity, what you're going to get is, this is v cos theta, and this is your v sin theta, right? Okay, from the impulse moment equation, we'll see what is the force that you're going to get in the x direction. By applying impulse moment equation, what you're going to get is mass per second, which is like rho av, the velocity in x direction, that in initial stage it is like a v cos theta, and finally at the end of your tip, what you're going to get is the velocity in x direction is v cos theta. Clear? But it is in opposite direction to the initial, so that's why what here we are getting negative. Okay, and if you simplify this, what you're going to get is the force in x direction is 2 rho a v square cos theta. Similarly, if you solve the same problem for the y direction, what you're going to get is 0. Why? Here we have the v sin theta, here we have the v sin theta. So if you simplify in the impulse moment equation, the both will get cancels, and finally what you're going to get is 0. Clear? And next, we'll see the next case. Here the jet strikes a curved plate or a vein at the end, but it is unsymmetrical. How can you say, or how can you remember that like it is a unsymmetrical vein? See here you have two angles, right? It is like theta and it is like pi. That means we have two different angles. Because of that, because of seeing that two angles, you can say it is a unsymmetrical one. Okay, in the same way, apply your impulse momentum principle or equation. That means the force in x direction equals to mass per second, which is like rho av. This is the velocity at initial stage, and this is the velocity at final stage. And now the velocity is having at the tip of your vein, and in x direction what the velocity you are going to have is v cos theta, and this is v sin theta. If you simplify this, you will get the force in x direction is rho a v square into cos theta plus cos pi. Clear? And similarly, for the force in y direction, here you have v sin theta, here we have v sin pi. So that's why you're not getting 0 here. It is not equals to 0. Why? Because the angles are different. You're going to get different values. Clear? So finally, the force in y direction is rho a v square sin theta minus sin pi. Clear? Thank you.